Hey friends, Ben again. Hope this finds you well. This is a video for Calc 1. We are looking about the notion of derivatives. And in particular, we are looking at derivatives by taking the definition of a derivative. If you have had Calc 1 in high school, you have to pay attention to something in particular here that maybe other people don't have to pay attention to. By the definition. So I'm demanding that you use the definition. You don't get to skip ahead and use the rules, which we're going to prove using the definition. You have to go ahead and use the definition. And I know it seems like I'm just kind of making you do extra work, but I need for y'all to understand what this definition is, what the derivative actually represents. Once you've got that, then we'll go ahead and use the rules after that. But all right, so let me bring up the old iPad here and we will tell it to screen mirror. And surprisingly, despite the fact that it's a Monday, I didn't have to install anything new. Weird. Okay, so our definition of derivatives, I want you all to think about this graphically. You have some particular x value, and you want to think about changing your x a little bit, right? So we are going to then take f of x minus f of a. So that means the difference in the height of this point here and this point here, okay? So f of x minus f of a, and then we're going to divide it by the difference between x and a, okay? So that's going to be the distance across there. What is that formula? That's rise over run. So you've totally done this sort of thing before, but the algebra is going to be maybe a little bit miserable, okay? So because the algebra is miserable, oftentimes we write it like this instead, and this probably looks more intimidating to you because of the delta x. But the delta x just means change in x. If y'all had some sort of physics class, you were not surprised by that, right? Because you talk about delta V and stuff like that for rockets. But it just makes things a little bit easier to write out the algebra of right here. So either one of these two methods is totally fine to do things with. If you're reading your textbook, you will see both methods used to write things out. So whichever one works best for you. I tend to find that most people can do that one there easier. So on the other hand, instead of slopes, we could instead be talking about velocities, right? And with velocity, you're talking about a change in position divided by a change in time. But in both these cases, we are then talking about a limit. And so that limit has your change in time or your change in x going to 0. Graphically, if you're talking about the slope example here, then we have to think about these two positions of x, and then we are moving the later position of x closer and closer and closer. And as we do that, the slope of that tangent line gets closer and closer and closer to the actual tangent line. And so the thing that we do in the limit is to figure out what happens when you get there, okay? So we looked at examples where you did that with sliders and got a good approximation earlier in the previous chapter, but now we're going to look at doing it using the notion of limits. So we are going to take a particular one here, and it's going to be our y being equal to the square root of x, and we're going to find the tangent line there at 2, 4, okay? And we're going to use our definition to do it. So I'm going to be thinking about this f of x being the square root of x, and I am going to, oh, I'm going to correct myself because I wrote 2, 4 here. And it was supposed to say 4, 2. Sorry about that. All right, so we are going to think about this and say f prime at 4, okay? And this over here needs corrected too. 4, 2. But f prime of 4 is going to be the limit as delta x goes to 0 of f of, this is too low or too far across there. It's going to run into my graph. So I'm going to do it here. F of 4 plus delta x minus f of 4, and we'll divide that by delta x. If you would prefer instead to say f of x and take the limit as x goes to 4, we can do it that way as well. It doesn't really make that much difference. So limit delta x is going to 0. Now we have to go see what f of x said. It said take the square root. So square root of 4 plus delta x minus the square root of 4. Y'all know that the square root of 4 is 2, so we don't have to just keep writing square root of 4. We can go ahead and write 2. But how do we tackle one of those? It's got those square roots. This is going to be multiplying by the conjugate. So I'm going to multiply by the conjugate here and write square root of 4 plus delta x plus the, I started to say square root of 4. Yeah, I'll go ahead and write square root of 4. You could just write 2. You don't have to do what I did there. So remember, we have to multiply by exactly the same thing on the top and the bottom. And now we can go ahead and say this is the limit as delta x goes to 0. And the bottom will have a delta x times square root 4 plus delta x plus square root 4. And then the top, we purposely were multiplying by a conjugate there to get this to do the right thing. And now we will have 4 plus delta x minus 4. It's a difference of squares then. The 4's will cancel. And now we have a limit as delta x goes to 0. Downstairs, it will be delta x. Yeah, you know what? I will just take that thing that I had right there, copy it, paste it, put it over here. All right. So then I'm going to take and cancel those out. And now I have a 1 on the top, right? And when I stick in the delta x being 0, I have 1 over the square root of 4 plus the square root of 4. So that is 1 over 2 plus 2. So 1/4. Okay. And I, for some reason, wrote all that in red. And I don't like that. So I'll just make it all match. So now writing the tangent line, we know it's got to be y minus y naught. So y minus 2 equals m times, so 1/4 times x minus x naught. And if you're wondering where that came from, that is your point slope formula, something from algebra. Now, if you'd like to leave it like that, that is a perfectly fine way to write your equation and nobody's going to object. But if you'd like to solve for y, you'll have a 1/4 x, let's see, minus 1, but then you'll add 2, so plus 1, okay? Yay, and that's getting your equation of your tangent line. The main big thing is being able to do this stuff here. and being able to do the difference quotient. Often you will instead have to do something with a polynomial, but I thought I would purposely do something with the square root because the square root problems are more miserable than the polynomial problems. So anyway. All right, let's take a look at something similar. And here we're going to find the velocity at the time when t is equal to 4. So if you recall, for velocity problems, we were going to say v of 4 is the limit as delta t goes to 0, delta s over delta t. So limit as delta t goes to 0, and we have to plug in our equation there. S of 4 plus delta t minus s of 4, and then divide that by delta t. Okay. Now, if you had a particular delta t in mind, you were maybe going from t equals 4 to t equals 5, your delta t would be 1, then you'd be doing that sort of thing. But we're not doing that. We're looking at instantaneous velocity. If that is not registering on you, that term of instantaneous velocity, think of it like this. You're going on a car trip somewhere. If you are going down the road and checking the mile markers, and at every mile marker, subtracting the distances that you went and dividing by the amount of time, and so on and so forth, you're finding the average velocity over that particular mile. Whereas if you just look down at the odometer, it tells you the instantaneous velocity that you were at right then. Okay. Never, ever, ever try to argue with the police officers about mean value theorem or something like that. And I was averaging 55 miles an hour, officer. Does not go well. Although when I was teaching in Oklahoma, one of our local highway patrolmen was a math major, and she would take people to task. It was hilarious. So, all right, limit delta t goes to 0. All right, we have to go in here and think about that s of t, and we'll have to say it is 100 minus 4.9 times 4 plus delta t, the quantity squared. Oh no, this is got to be too large there. Okay, minus the quantity, 100 minus 4.9 times just plain old 4 squared. And then we'll divide all that by our delta t. All right, so with the subtraction portion, you can see pretty easily that the 100s go away. But the other piece of it is not so easy. We'll have to say minus 4.9 times 4 plus delta t squared. Let's see, squaring that will be 16 plus 8 delta t plus delta t squared. And then we'll say minus a negative 4.9 times the 16. All that divided by the delta t. There's a limit. Delta t is going to 0 here. And gosh, I, embarrassingly enough, have to go grab a calculator to find out 4.9 times 16 is 78.4. So negative 78.4. Started to say plus, but it's minus 8 times that. Well, that would be 39.2. And that's delta t. And then minus 4.9 delta t squared. And then plus that 78.4. And delta t here. So now we're going to cancel the 78.4s. And what I need for you to spot in our limit delta t going to 0 is that we have a factor of delta t across the entire top. If you want to cancel something, you have to factor it first, right? I'm going to factor out a minus delta t times, and then we will have the 39.2 and plus, because I pulled out the minus there, the 4.9 delta t. All that divided by the delta t, and then we'll cancel these delta t's. Have to cancel a factor, right? And then you're allowed to plug in the delta t being 0. And you'll have 39.2, I'm sorry, minus of 39.2 and minus 4.9 times 0. So you have minus 39.2. And I think for a problem like this, we're probably talking about meters per second for our units. So anyway, that gets us the idea here. You have to go ahead and do these limits as delta t or delta x or whatever goes to 0, but it's mainly just doing lots and lots of algebra, all right? So let me show you all something. Now this is verging into what mathematics is about past the calculus. What we mostly do is to try to show things are true that we suspect are true just by using logical inference. And so I'm going to take this and do, oops, I guess I should do it like this, f plus g. So I have a function called f and a function called g, and when I put them together, the new function is called f plus g. That's not anything amazing, I know, but I'm going to talk about this having the limit as delta x goes to 0 of f plus g of x plus delta x minus f plus g of x, all that divided by delta x. Okay. Now we have a limit as delta x goes to 0. We have to think about what f plus g of x means. And all it means is f of x plus delta x plus g of x plus delta x minus f of x and minus g of x. So all that divided by delta x. If you rearrange it, then you got f of x plus delta x minus f of x. And I'm going to break that out on its own. And g of x plus delta x minus g of x. Break that out on its own. And we should remember that those are our definitions for f prime and g prime. Okay. So now that we know that when you take the derivative of a sum, you can just take the derivative of each individual part. Now we can do that. You cannot do that with multiplication. If it's f of x times g of x, you will not get the same thing, okay? But you have a couple of nice rules like this. Also, if you take a constant times a function, you can just factor the constant out, all right? So now that you have that rule, you can use it. Yay. Then there's a little something that we ought to work out because it's going to show up in the classwork that you're going to do, and it may not be super obvious what I'm wanting you to do. So if I ask you to calculate x plus delta x to the nth power minus x to the nth power, what you need to remember is how squaring goes. Or how cubing goes. And when I say remember it, I'm fully aware that you may have not encountered this before, but you should have, okay? With squaring and cubing and so forth, if you did a fourth degree, there is a pattern that's going on here. You always get that power first, and then you get n times, and you reduce the power by 1. So when I say this to the nth power, it should start with x to the n plus n times x to the n minus 1, and then times a delta x, plus there's a lot more terms, and they all have a power of at least 2 delta x's in them, minus our x to the n. So these x to the n's cancel. And then this is equal to n x to the n minus 1 delta x times other stuff that will have a 1 plus a delta x times some things, because all of the other powers or all the other terms will have more than 1 delta x in, okay? And now when you're doing a limit later, you're going to spot that you have this term to cancel, and that all the stuff later that you plug a delta x into will vanish. And that's why you'll have this n x to the n minus 1, okay? So that's one of the problems that you're going to work, and you'll get it. It's not too terribly rough, but that guidance I just gave you there about the algebra could be helpful. So this here is something similar. I want you all to spot that if you rewrote this very slightly, e to the x plus delta x, just like if we said e to the 2 plus 1, you could write that as e to the 2 times e to the 1. Well, if we got x plus delta x, you can rewrite like that. And then this is really e to the x times e to the delta x minus 1, okay? So as delta x goes to 0, then this stuff here is going to go to 0, but you're going to do things in a difference quotient, and you'll have a special thing about your limit, okay? But other than that, all very doable, okay? And so I am actually going to stop there. And then on Wednesday, y'all are going to be looking at some of this stuff in class. And it's just working through some limits like this. It'll be a little bit confusing at first, but you'll get it figured out. It's not too terribly rough. Okay. All right. I will see you all in class.